everybody to the January FPGA seminar. And so today we're going to have Jeff talk about experience with Bluespec. And I know there are people I know would swear by Bluespec as the best thing to going, and we'll see if Jeff has the same thoughts about that. Thanks.
Okay, welcome. Thank you for coming. So just before we start, a disclaimer. So I'm not an HLS expert. I do applications. And I'm going to talk about a couple of different tools a little bit. I haven't necessarily used all of them, so some of this is secondhand. And of course, opinions are my own, and we're welcome to discuss at the end of the presentation. So what I'm going to do is pretty much three primary parts. I'll give an introduction about sort of high-level synthesis, where Bluespec fits into the landscape, what makes it different. Then I'm going to change gears a bit and talk about my own thesis research so you understand what I actually did with the language to sort of feed the experience I'm sharing with you. And then I'm going to throw a little bit of code up on the slides to show how you actually go from Verilog to Bluespec and sort of try to demonstrate some of the neat language features and how concise it can be. And then I'll just wrap up with a couple slides of summary. So first controversial statement, programming FPGAs is hard. We always hear these complaints at FCCM, FPGA, and whatnot, and there are a number of things that people are trying to do to make that easier. So, there's a lot of people in the room working on overlay architectures, better CAD, faster place and route, latency and sensitive design, better devices, what I might call magic, sort of imperative language to gates synthesis. One thing that seems to be missing from that landscape is really a better hardware design language, a better design hardware with, which is really where Bluespec fits in. So the problem solved for the gates really is you have a recipe here, you've got inputs, an algorithm, and outputs, and you really want to change that into a layout that makes that happen. And when you think about it, asking any sort of algorithm to go from a recipe to a kitchen layout, and the tools and the staff and the specializations, the synchronization, it's really a pretty remarkable thing. And so maybe what we really want, or at least there's place in the ecosystem for a better way to just do the layout. Right? And of course, that's often referred to as the semantic gap. So going from do this, then do that, then do that, to here's a layout that makes it happen. Right, so high-level synthesis as it exists currently, there's Impulse C, Catapult C, this C, that C, Vivado HLS, which is I think C and C++ based, and then of course our own homegrown leg up. There's also two Java-based systems that I'm aware of, so there's Maxillr MaxJ and IBM Lime. And there's also, of course, well-established MATLAB-based tools for DSP. And of course, Altera OpenCL as well, so taking an explicitly parallel imperative description and going to hardware from that. So what it seems like to me is you really can't have it all. So the successful languages that I list here really work on certain types of problems. So they're really good for data flow, for instance. All right, if you take system generator, you hook this block to that block to that block, it can generate it for you, it can do fairly well. Maxillr, they say pretty much what they do is extract data flow graphs from Java. Altera OpenCL, of course, is an explicit kernel, and then LegUp and Vivado work on embedded applications. So basically, we know how to do data flow fairly well. What about control? What about memory controllers, switches, network on chip, I/O, stuff like that? It's not really clear how you do all that in an imperative paradigm, how you get really, really good performance. And so the question is, what about hardware designers who are comfortable with clocks, resets, concurrency? What do they have? I think we'd all agree Verilog is pretty nasty for all that stuff. It takes a lot of code to get things doing, and then it's very brittle. So Bluespec is not an imperative language. It is not a way to take a software designer and make them a hardware designer. And it's not a way to get out of designing architecture. You still have to think about architecture to get performance out of Bluespec. But what it is a productive language for hardware designers. It's a better way to express an architecture. It's a faster way to explore your architecture and to simulate it. And it's much, much more concise than Verilog and VHDL, as well as having a lot of nice things that your compiler can do for you to help you out. So it is a hardware design language. You instantiate modules, not functions and variables. You have clocks and resets. Anything you can do in Verilog, you can do in Bluespec, which I think is quite interesting, actually, because a lot of HLS, in exchange for much greater ease of use, there are things that you can't get through the abstraction to do. Whereas Bluespec, you are explicitly instantiating everything. If you don't ask for it, you don't get it. and it lets you explore microarchitectures really quickly. I know Intel, in a talk here maybe 2 years ago, was saying they're using Bluespec for processor designs and so on. One of the other interesting things is it's a powerful enough language you can actually use to model your system before you have a detailed design, so you can kind of rough in what a block might do and what latency it might have and then integrate it with the rest of your system, which I find that people don't generally do with Verilog. Normally you write a C model and then you try to port that. So the key analogy I would give you is that Bluespec is RTL as C++ is to assembly, in the sense that you can do the low-level bit hacking type stuff. You can get very close to the metal. You can do bit and cycle accurate simulation. In fact, everything that happens in Bluespec is bit and cycle accurate. It seamlessly integrates legacy Verilog, but on the other hand, you don't get any overhead. So unless you ask for it, it does not get instantiated. So that would contrast with something like Java, where you have a lot of automated stuff going on behind the scenes. C++, like Bluespec, don't ask for it, don't get it. So it's very lean in that sense. But it's also a high-level language, so it's very concise. It's very easy to compose things correctly. It really promotes abstraction and reuse, library development, correctness by design. It simulates really quite quickly. I would place it at 10x or faster based on what I've done in my work. And it also gives you a really helpful compiler. So sometimes you get a message in a Verilog and you don't know, what is this, why is this happening? Bluespec will give you sort of a higher level of, why is this not working, or why don't I like this code? So the history of the language, it came out of research at MIT's Computer Science and Artificial Intelligence Lab with Professor Arvind. It started off with Haskell, which is a functional programming language developed at Microsoft Research, among other places. And what's interesting about functional programming is it makes a really strong distinction between pure functions, which always return the same value given the same arguments, and things that have state. And by making that separation, you can kind of reason about the things that don't change state separately, which is really nice. So out of that, they founded a semiconductor called Sandburst in 2000, designing 10G Ethernet routers. And they sort of developed Bluespec, or something like Bluespec, as an internal tool to help them do that. That was fairly successful, and they actually founded a company to create Bluespec and the related tools in 2003. So they've been around about 10 years. I think they've had several rounds of venture capital finance, and they're starting to get used in industry quite a bit, as far as I know. So we'll just change gears a little bit here, and I'll talk a bit about my research so you understand what I've actually done with Bluespec to kind of come at the conclusions that I've made about it. So in 2010, actually, I started learning Haskell for personal interest. I read a book, 7 Languages in 7 Weeks, just trying to kind of expand my programming repertoire. And I was really fascinated by the idea of functional languages. And then in 2011, I went to apply for my Master of Applied Science here, and I started poking around for things that I might want to research, and that's where I came up with Bluespec. Basically, I was looking for Haskell, functional languages, synthesis, and it turns out that had actually been done. So in mid-2012, we got a Bluespec license in-house. It's free, so that's not really a barrier to adoption. Started tinkering with it. And really the primary focus from mid-2012 onward was focusing on the software model that I'm going to talk about in a second. March 2013, I started writing hardware code for my thesis. September, it was done, debugged, validated, and defended the thesis. I was a little bit scared around March because I decided to use a new programming language to write my thesis with 6 months to go. And that was actually a gamble that paid off really well. And obviously could have gone otherwise. But I'm glad I did it for sure. So the subject area is biophotonics, the study of light interacting with living tissue. It's useful for a number of things in medicine, so clinical detection and treatment of disease. But the problem really is that light is scattered quite a lot as it moves through tissue, anywhere between 10 and 1,000 times per centimeter of path length traveled. And so to get a good result, you need to actually understand how that scattering happens and model it. So it's both crucial and very compute intensive, which becomes a bottleneck for a lot of biophotonic techniques. So one of them that produces some pretty cool pictures is bioluminescence imaging. So you tag cancer cells or sometimes infectious cells, viruses, bacteria, whatever, with a bioluminescent marker. And you image it with a low light camera, so whatever organ is infected will actually emit light on its own. You immobilize the animal, in this case a mouse, and you image it with a low light camera, and you can actually watch the disease as it's spreading. So you can see here we've got a little mouse. This is a map of the light being emitted from it, so there's actually a cancerous tumor, which you can't see on the CT scan here. But here's an internal model, and there's the dissection actually showing, yes, there is indeed a tumor where they thought there was. And then on the right is actually a simulation that I did with my software that shows a similar thing. So there's a tumor inside a mouse and what pattern of light you see on the surface. The main focus that my co-supervisor is working on is PDT, photodynamic therapy of head and neck cancers. And that's a treatment where you take a light-activated drug, and where light hits that drug in the presence of oxygen, cells die. And so it's obviously crucial to the effectiveness of this treatment to simulate the distribution of light throughout the tissue in a highly heterogeneous structure. So here's an example of a head and neck cancer, the tumor actually marked. And so as you can see, there's a lot of anatomy going on there. As we know, the head and neck has a lot of critical structures. And so if we don't know where the light's going, we don't know what's getting killed, and the outcome for the patient could be very, very bad. So we started with a gold standard model called MCML. It's a Monte Carlo method for ray tracing photon packets. And so what you do is you just repeat a whole bunch of times. You take a packet of light, you launch it in some direction randomly determined. You choose a step length that it travels before it has an interaction. It figures out what region it's in, determines if it's hit a boundary of a region or not. And if it hasn't hit the boundary or region, then it drops some of its energy where it is and then scatters off into a new direction and repeats. It could also hit a material interface, in which case you might have reflection, refraction, or just a change in how it propagates. And following that, it might also exit the volume. We also have a termination scheme called Russian roulette. So as the packet weight drops, it adds less and less to the output result. And so we eventually just randomly terminate it. All right, so we're doing this with a tetrahedral mesh geometry, which is very compute intensive. We're launching up to 1 billion packets. Each packet traverses that inner loop 100 to 1,000 times approximately. PDT plan to optimize might require anywhere from 10 to 1,000 iterations of that outer loop. And so in total, you're traversing this inner loop up to as many as 10 to the 15 times, each of which involves a number of operations, calculating sines, cosines, intersection of a ray with a face, and some logic associated with that. So that's quite a lot of computing. It would take, we think about usually half an hour on a highly optimized single CPU system per inner loop. And so you're looking at maybe 500 hours to plan the treatment for one patient, which is quite a lot. So in August to about December of 2012, I wrote the software version of this. It's the fastest Monte Carlo tetrahedral mesh software available. It's C++, multi-threaded, SIMD optimized. Worked a lot with the data structures to get it really tight. So basically, for the hardware acceleration, we're starting with a very highly optimized baseline. That still takes about 30 to 60 minutes per simulation to get acceptable output quality. So that's really not fast enough for what we want to do with this if you have to run that simulation 1,000 times. So we want to accelerate that. What already exists, so William Loeb, who was here, and some of you may have been students with him, implemented this in an Altera Stratix 3 for what's called MCML, which is infinite planar layers. So if you have a structure that looks like this, where it's just a layer on top of a layer, with radial symmetry like that, works just fine. So that's been done in FPGA, it's been done in GPU. There also exists one voxelized representation, so you just chunk the volume up into voxels. And so one might say, good, we're done, we have everything we need, right? Not so much. I mean, real living tissues don't look like this, they don't look like this. Real things look like that. They're complex, they have curved surfaces, they require a lot of information to describe. So here you might be dealing with tens of layers, thousands of voxels. This is 300,000 tetrahedral elements in that mesh. And that's actually the house that's commonly used for imaging experiments. So this has been done in software, in OS. I basically improved on that, got about 5 or 10% speed, but it's maxed out at that speed. There is no work on accelerating that on GPU or FPGA up until. Right? So what I did is I took this and I put it on FPGA. So going back to this pipeline, took this, it's basically fully unrolled. It attempts one hop every single clock cycle. And where there's branching of the of the data flow there. So you can see you've got two things that go into step, and then three things that go into region lookup. I just queue it up, with the goal being 100% utilization of the hop core, because that's the one that actually takes the most DSP resources, and it's also part of all the different cycles in the control flow there. I've also reduced the latency a bit, because obviously the more latency you have in the pipeline, the more balancing registers you need to insert. And so what I did is I actually queued up the distributed random numbers. So if I need a randomly distributed unit vector or exponentially distributed step length or whatever, calculate that first, stick it in a queue, and then at point of use I can just pull it out with no latency. All right, so as I said, it's the first and only hardware accelerated tetrahedral MC. The moving parts, it's got a random number generator, of course. Can't really do Monte Carlo with that, without that. Some math functions, so rolled my own logarithm, quartic sine and cosine, and Haney-Greenstein function. Reason being that I wanted a very particular reduced precision, only 18 bits, and I didn't need floating point. So with that, I also did a square root core, matrix multiply, re-tetrahedron intersection, divider, all the pipeline queuing, the flow control, and did the fluence accumulation, so block RAM, read, write, and so on. Yep.
Does Bluespec have library versions of these state trait functions that you
not that I know of. I think there are some freely available here and there. Part of writing my own was also just getting familiar with the language, seeing what it can do. So there may be room to do better on that. I haven't exhaustively searched. So the bottom line, all this written in hardware while learning the language, 6 months. It took 4.5K lines, including everything. So that's all the comments, all the test benches, implementing it and debugging it. So I would probably still be working on that if I was doing this in Verilog, that's my feeling. And it certainly wouldn't have come to as little as 4.5K lines. So I took that, simulated it, validated, placed and routed on a Stratix 5. Slowest block ran at 325 megahertz. The unoptimized system all jammed together runs at 215, which I think it's a decent result, but there's certainly a gap there that could be addressed by better pipelining between the stages, which I think will be quite easy to do. Net result is it's 3x faster than a quad-core Sandy Bridge with this highly optimized baseline implementation. That's for a single pipeline. We fit 4 of those on the Stratix 5. So that should scale to about 12x performance and hopefully 15 plus when we can address that system clock. So it's a work in progress. Next step will be tuning it, scaling it up, and then I also want to implement a custom memory hierarchy so we can fit even more mesh elements and even more parallel processing cores on there. All right, so the summary of that is I found it a very productive language and the learning curve was not particularly daunting. You can basically start writing what you would write in Verilog in Bluespec and then start getting into the more interesting features of the language. So now I'll try to keep the code examples light, but I do want to show some of the neat stuff. So going from Verilog to BSV, the design methodology is basically the same. You're designing a hierarchy of modules. So it's not writing sequential code, it's not writing imperative code, it is a hardware design. The expression syntax, constants, a lot of the constructs, if then else, etc., is just Verilog, so that's all very comfortable. There's the idea of blocking and non-blocking assignments, but you don't have an assigned statement. I'll show you what you have instead. What's different is you think of what happens in terms of actions and rules. So in functional programming languages, you have pure functions, which always return the same value regardless of any outside state. They don't change any state. And you have state elements. So in Bluespec, you have state elements, so you've got your registers, FIFOs, block RAMs, etc. And you have rules which describe how you transform your state elements. It also has a nice separation of interface and module, very strong type system, which is also inherited from functional language. And I found eliminated a lot of different errors. Because Verilog will be kind of sloppy, right? Signed, unsigned, it will automatically extend and truncate, and that can really bite you sometimes. And it also has a really neat polymorphism mechanism. It's a bit different from C++. Okay, so Verilog, a register. What does that look like in Bluespec? It's like that. So one of the interesting things, and one of the things I really don't like about Verilog is often you find yourself coding a template, so it'll infer a thing. Why don't you just tell it build that thing? So Bluespec, you just say make a register, literally mkreg. And then assignment looks exactly the same. So if you want to increment, assign r to r+1, and it does that. Right? And I find it provides better clarity. There's less boilerplate. The code is more compact. So instead of having this if-then-else statement that you have to kind of parse and template match and say, okay, I know that's a register, you just say, yes, I have a register.
And how
Yep.
do the reset signals determine?
The reset is actually implicit. So these two sections of code are identical in the sense that if reset set r to 0, this one 0, and there's a default module level reset that you can override if you want to. But typically, I don't know, my designs at least, there's just one reset. And you can do the same with clocks as well. So this is all on a default clock, but you can handle multiple clock domains. And it is inherently supported by the language.
So you're saying you have one default unnamed reset? That's basically what you're saying for that syntax.
Yes, so when that goes out to synthesis, so if you want to synthesize that module, it will just put out a reset. And so every time you have a reg, there will be a reset signal for all the regs in that module.
Does the language specify its name? Does it have a specific key?
Yes.
name?
Yeah, when
So
it's
you can set-
instantiated, I think it comes out as RST or something like that.
So you can set timing constraints on that call,
Yes.
so reset and so on.
Absolutely, yeah.
But R is the reset signal, right? That's what that one line says.
R is the register name. All right, so what it's saying is, okay, so this is a register. It holds an unsigned integer, 8 bits, named R. And then this is the sort of the instantiation operator, if you want to think of it. So R is bound to an instance of a register with a reset of 0. Make sense? Fine.
So let's say I wanted to use a different reset. I have 50 resets in my design because I'm a bad designer. Would I just write another rule? Is that the way I would do it?
It's not a rule. There's a language construct to say this reg takes a different reset. I haven't really gotten into it. I haven't had the need.
Could
It exists.
Could you write it as a rule? Seems like if I, like say, I don't know, I guess it's just a question. If I wanted to write my own reset and I didn't know how to do that, could I write another rule and it would just figure it all out?
I don't know. I haven't used multiple resets. But I do know there's a language construct that lets you specify the reset on a given instance. And same for clocks as well. Okay. So one of the really, really fundamental things that Bluespec brings to synthesis that I think is a really powerful concept is the idea of atomicity. So you can have an atomic action. It's very similar to a database transaction in the sense that there's the state before the action executes, there's whatever changes it makes, and nothing can kind of mess with that in between. So it executes instantaneously, and it makes sure that no action can conflict with another. Right? So in Bluespec speak, we would say it fires only if the side effects are conflict-free. So let's say we have an action here where we increment A and decrement B, both A and B being, let's say, registers, although they could also be wires. And we have another action that sets A to 0. So obviously the side effect here is an assignment to A, and the side effect there is an assignment to A, and so there's a conflict between the two. And the compiler actually knows that those two things can't happen simultaneously. Okay? So now rules are basically actions plus conditions. And so it's kind of similar to a Verilog always block, except it's far more powerful. Right? So basically a rule is something that is always trying to fire. But it will only fire when it's able to fire, when its side effects are compatible with everything else that's going on in the system, and when its explicit conditions are satisfied. And so the compiler generates a schedule for this. So in Verilog, if you have a register, you have two things that want to update that register, you have to write logic that says who gets to update when. And you've got to mux it, right? Whereas in Bluespec, you can just have a rule that writes to it, another rule that writes to it, and the compiler will give you a schedule that actually makes sure that only one thing updates it at once. So let's do a simple example here. So we have a rule. Let's just say we have a counter here that's running free, right? So every 5th time it enqueues a 5, every 3rd time it enqueues a 3 into a FIFO. And we'll take for granted that this is a FIFO enqueue, right? Now logically, can we enqueue two different things into a single FIFO at once? No. So intuitively, there's a conflict here, right? And so when counter hits 15, it's going to try to fire this rule, it's going to try to fire that rule. All right? So we have an explicit condition on the rule there. We also have an implicit condition, which is you can't enqueue to a full FIFO, and only one thing can enqueue to a FIFO per clock, which kind of conforms to our intuitive sense of what a FIFO is, right? So when you go to compile this code, this is what you actually get from the compiler. It says rule enqueue every fifth was treated as more urgent than enqueue every third. Conflicts. Fifth can't fire before third because FIFO enqueue and FIFO enqueue. So it's saying that they're both trying to enqueue the same FIFO. They can't do that at once. And it has arbitrarily broken that tie just by taking the first rule that it sees. Right? And then it says likewise every third can't fire before every fifth because within the same cycle you can't actually do both. Right? On the other hand, it did create a Verilog file. It's just telling you I had to make an arbitrary decision. I don't know exactly what you want. Okay? So that's actually kind of handy. Yes?
Can you tell it exactly what you want?
Next slide.
Okay.
Paul?
What's the semantics, what's the 5, like the argument to that?
That's the value that's in queuing.
Oh, okay.
So I'll get into how modules and ports work, but for now, so you have a FIFO called myFIFO, you're enqueuing a 5 or a 3. Fine.
So maybe get this later. This would all be written inside the modules. These are all
Yes.
local signals and so on. So it's all using still the same kind of hierarchical constructs we're using.
That's right. So the only place that state can exist is inside a module. And so, so all these rules would be inside a module, which would have a register or a wire called counter. They would have a FIFO instantiated called myFIFO, and those are all local to that block. Yeah.
Question. Just
Yes.
these rules are checked on every clock cycle, so this rule notion is sort of a sequential logic thing.
Yes.
And how do you want to specify a large combinational chunk of logic? Is there, do you use rules for that, or there's some other language construct for that?
You can specify all kinds of sequential logic inside a rule.
A combinational logic?
A combination, yeah. And that's fine. It's just like having it inside an always block in Verilog.
Sure.
The difference is that you can't assign twice to the same register in different always blocks, right? Because you're going to get a conflict.
Yeah.
Whereas you can do that in Bluespec, and then the compiler will actually determine which of those always blocks, or which of the rules, sorry, is permitted to fire. So in Verilog, you have to arbitrate between the conflicting accesses. In Bluespec, you just make the conflicting accesses, and the scheduler will resolve which one can do what.
So
when.
these rule conditions are always kind of at a checked at a clock edge.
Yes. So every clock, the scheduler will look at what can fire,
Yeah.
then it will look at its conflicts, and it will choose what does fire. Yeah.
Do you have any idea what would happen if instead of 5, if you hit a conflict, you know it at compile time?
Yeah.
But what would happen if the 5 and the 3 in the condition were from a register?
We're from a register.
Yeah. You
That's
know-
fine. It'll read the register and stick the value into the FIFO.
But you wouldn't know about the conflict, right? At compile time.
Oh, sorry. This 3 and this 5.
Yeah, that 3 and that 5. Yeah, in the condition, what would happen? If
It would know that it could conflict. It's conservative. If it's possible to conflict, it will schedule them.
And I guess we're trying to figure out what kind of hardware would that build. Would that
Right. Can I come back to that on the next slide? Okay. Okay, so we got this compiler warning. It says, I don't know which one you intended to be higher priority. You can actually give it a directive that says descending urgency, queue every fifth and queue every third. Right? And so it says when those rules conflict, treat and queue every fifth as more important. All right, so when it's 3, 6, 9, 12, it'll enqueue a 3. When it hits 15, it's going to enqueue it'll enqueue a 5 because this rule overrides this rule. So in terms of what hardware it produces, it will evaluate the guard there. It will say counter mod 3 is mod 5 is 0. So this rule is enabled. It will do counter mod 3 is 0. And so this rule will be enabled. And then it will say, okay, both these rules could fire, except that we have a conflict and we've specified in the event of conflict do this one. Does that make sense?
I guess that means like a mux in front of the 5.
Yeah, so it would mux the input to the FIFO and it would mux the FIFO enabled. Great.
And so in this case, it's just going to, let's say on clock cycle 15, it's just going to enqueue 5. It's not going to enqueue then 3 on the next cycle.
No.
So it also forwards the two conditions together and makes a clock enable pretty automatically.
Basically, yeah. Yeah, so you'll notice here that I don't do anything involving that FIFO clock enable, write enable. It actually comes out of the module declaration there. Okay, so in this case, because we've specified the urgency, it's unambiguous now what to do when both conditions are true. It says every fifth is more important than every third. So if you wanted, what you asked on, if you wanted it to enqueue the 15 on the next cycle, you would have to explicitly insert logic to do that. And that's that principle of you get what you ask for and no more, basically. Okay, how about this one? So we want to enqueue counter when it's an even number. We want to enqueue twice the counter when it's an odd number. Compiler says, no problem. It can prove that that condition and that condition are mutually exclusive. And so it doesn't actually need to do arbitration there, which is pretty neat. You can also put assertions about rules. And so you can say, for instance, this rule enqueue stuff should fire when enabled. Okay, so enqueue stuff if n, so we have an enable signal n, and then we have an action, my FIFO enqueue some value, right? And then we also have a method, which I'll get to in a second, that says my FIFO enqueue I. Does anyone want to hazard a guess as to what happens here? So this is asserting that every time this rule is enabled, it should fire. Is there a problem with the code? Or equivalently, what could prevent this enqueue from happening?
Checking overflows for you.
Yeah.
Like will fall.
And?
Clarification, first of all. From the slides you showed before, it sounded like rules are things which always try to fire when their conditions are true. How is this any different, first of all? What's this
The method?
No, this fire when enabled. I thought this would, it sounded like that's what rules are supposed to do anyway. Well, what's going on?
No, this is no special case of a rule. It's just I've included an assertion that every time this condition is true, it should fire.
But isn't that what rules always do anyway? Like when you say a rule saying, here's a rule and here are the conditions on which it's supposed to fire, why do I need that special thing? Isn't the rule just a list of code plus a condition?
Because it could be enabled in terms of the condition you give it, but it could have a conflict, and that's actually where I'm going with this. So what the compiler says to this is, so we have this method put, right? And it says it's treated as more urgent than enqueue stuff, because you see there's a conflict here. There's two things trying to enqueue. So if I call this method and I try to put something in there, that's going to preempt this rule from firing. And so we have a condition where the rule is enabled, but doesn't fire, which violates the assertion. Does that make sense? So basically, if you're writing some sort of static pipeline of some sort, and there's a step that you want to happen every single time, you can say, I want this to happen every single time, and the compiler will actually tell you if that's not possible. And it will actually, in your simulation, generate code that will check that assertion. So even if you put a, say like a Verilog module in this, where it doesn't know really what's going on, it will still be able in simulation to check that that assertion is true. One?
Could you walk through the method syntax and just with all these?
Sure. So, actually, I'll get to methods next. But basically, the idea is instead of ports, so in Verilog you have ports, which are wires going in and out of your module. In Bluespec, you don't have ports, you have methods. And so it's kind of like an object-oriented paradigm, where the only way you interact with your module is through its methods. And so in this case, you have a method. When you call that method, it tries to enqueue something. Yep.
So enqueue is a method then?
enqueue is a method, yeah. And I'll actually get into that in greater depth next slide. All right, so you get the idea that there's two things trying to enqueue into a FIFO, and intuitively only one can do that at a time. And so that blocks the fire when enabled. Okay? So as I just said to Vaughn, ports are replaced by method calls, of which there are three types. So you can have a function method. And remember, function in the functional programming language sense is a pure function. It makes no alteration to state. And so in that case, it's something that can always fire, it has no side effects, and all it will do is query the state of the module. So you can ask it if it's ready. And intuitively, you should always be able to ask a module if it's ready. There's nothing that would prevent it from answering that question, right? You can also have an action. So the put action I showed earlier, an action is something that changes state. And because it changes state, an action might be blocked because something else is trying to change the same state in the same cycle. Right? So an action can carry implicit conditions, and those implicit conditions are actually passed backwards to the caller in the way I'll explain in a second. So FIFO and Q I've been using as an example of that. Right? And you can also have an action value, which is action that returns a value. So that can do two things. First of all, the action component of it can change state. And the value component of it returns a value, but you can also put a condition on this. So let's say that you have a pipeline that takes 10 stages, right? You stick something in the pipeline, 10 stages later you get an output. You can set it up so that that action value will only return when there's actually a valid value at the end of that pipeline. Does that make sense? In that case, it would be sort of like an output valid type logic, right? So I'll illustrate this with an example. If we were going to do a FIFO in Verilog, it would look something like this, right? So we would have to declare all the different wires that carry our signals around. We instantiate a FIFO, tell it the depth, give it a read enable, write enable, data in, data out, ready. And then in this case, if the FIFO is ready and there's valid input data, I want it to fire. I want it to enqueue that value. Right? So I just AND the ready with the valid input, and then I assign the value to the incoming value. Right? Okay, what does that look like in Bluespec? It's rather nice. Right? So what you do here is we instantiate a wire, which is going to carry our incoming data. All this stuff, all these wires, and this module instantiation actually just go to that one little module instantiation in line 2. And then all the logic here is just a rule. Right? So the rule, enqueue value when valid, is fairly descriptive. Right? So we want to enqueue that value. And then we can have other stuff inside that rule. Right? Let's say that we have some logic that we want to happen only when the FIFO enqueues. Well, it's fairly simple to do that in the sense that this has to be atomic. So only if the enqueue is permitted to proceed do we actually do the other stuff inside that rule. Whereas here we would have to say, we'd have to have an always block that says if FIFO ready and I valid, then do all this stuff. Here the conditions are actually carried implicitly. Go on.
Why do you have a let in one case? I mean, you're making various things, right? So you're making wires, you're making FIFO before you made the FIFO had a let statement. I think none of the other ones had that.
Yes.
What does let mean?
One of the nice things, one of the conveniences of Bluespec is the strong type system. And so every expression has an unambiguous type. And so in this case, it knows the type returned by make size FIFO 16. And so it's kind of like the auto keyword in C++ 11. It just means you figure out what type BSV FIFO is. I could equally well type FIFO pound bracket uint 8. Right? Because obviously val is a uint 8, so we must stick a uint 8 into a uint 8 FIFO. Alex?
What about MK wire? Can it take an argument saying what kind of, can you put the uint 8s on the MK wire side similarly and use let
Nope.
on that first line?
No, there's no need to. Right? So MK wire returns a wire, but again, because of the strong type system, you know it's returning a uint 8 wire, so you don't need to tell it that twice.
Oh, can you maybe say it once, but just change it so that there's a let's on the left-hand side?
I think you could do that if you were assigning a uint 8 to val somewhere else.
Oh, okay.
Does that make, like you have to tell it somewhere what's going in the FIFO.
Yeah, I'm just wondering if MK wire also accepts an argument. MK size FIFO accepts an argument, so why doesn't MK?
Because there's no argument, it's a wire.
Yeah, that's not the size, it's the depth.
Or the type, sorry, the type of the stuff it's carrying.
Yeah, the type of the wire is the uint 8. And so we're saying val is a uint 8. Oh, sorry, you know what? There's actually a mistake on this slide. It should be a wire pound uint 8. My apologies on that. Okay?
Because you figure MK wire will accept an argument saying this is from strong type system. You have to say somewhere the type. So.
But if the type is on the left-hand side and you're assigning
Yes.
it, what's on the right-hand side must be of the same type. Okay? So sorry, there is a mistake there. That should be wire pound uint 8 because it's not a uint 8 value. It's a wire that transmits a uint 8. If that makes sense. Apologies on that.
So the size of your FIFO is its depth, so the width
Yeah.
is automatically computed?
The width is automatic from. Okay, so actually, this is a good example of inference at work, right? So val is a uint 8. We're enqueuing val, so the FIFO must hold uint 8. And it knows the bit width of uint 8, so you don't need to tell it. Great.
Could I, in different rules, enqueue different sizes in the FIFO, and it would just make the biggest size of that data?
No. No, that's part of the strong type system. You get no implicit conversions at all, which may be perceived as a bit of a pain, but it also prevents you from shooting yourself in the foot. Jason?
So for the rule, if you value and valid, that's the name of the rule. Do you need to also have the valid signal there so that it only activates when valid?
No. Wires carry an implicit valid signal. And I'll give a code example of that a bit later on. So yeah, you can see there's a lot of stuff that actually ends up implicit coming along for free. Jonathan?
Well, on that note, the Verilog on the left-hand side is incomplete, right? Like there's no
Because-
register, there's a thing storing this thing, but it is the thing on the right-hand side building the full FIFO for it. Maybe I'm lunch.
I don't think I understand the question.
I think it's, remember the FIFO instance is basically calling another module, so you're not seeing all the modules.
Yeah, MK-sized FIFO instantiates a
I'm missing the
FIFO.
FIFO inst, I see.
Yeah.
So there's more Verilog in the instantiation of FIFO inst. Is there more Bluespec on the right-hand side?
No, this is complete.
Okay, so the compression is much bigger than what you're showing here in terms of lines, right? You need another whole FIFO thing.
Oh, I'm assuming, like, so the MK-sized FIFO is coming from the Bluespec library,
Nice.
and I'm assuming this is coming from Altera Megafunction or whatever.
Okay.
Yeah, so I mean, yeah, there's call out to a library here, there's call out to a library there. But in terms of instantiation, both are complete and both will enqueue a value into the FIFO. It's like kind of a nice compression of the code.
So are things like big size FIFO then are, they're library calls and not keywords, you can extend it yourself, if you
Yes.
sound like it, and so on?
That is just a module instantiation.
Okay.
So this is a Verilog module instantiation. You can write your own modules, your own ports, whatever. MK-sized FIFO is a Bluespec module instantiation. That's how you write your own. So it's kind of nice, right? You don't have to explicitly make all these control wires visible. You just interact with the methods, and the synthesis tool will create the underlying logic to do that.
Can you just quickly go over the iValid? Like, does every value you create implicitly have like a valid signal associated?
Not everyone. There are a number of instances where they do, which I will try to illustrate a bit later. That's okay.
And what does that represent?
iValid?
Yeah,
It just means there's a valid value there.
a new value there.
I guess what it means is really implementation dependent, but there's a notion of valid, right? Like let's say you have some sort of data processing pipeline that only gets new data every so often. You only assert iValid when you have a new data in. In the case of wire, so the wire is physically it's a wire, so it's a zero latency connection zero clock cycle latency connection from A to B. But in Bluespec, the meaning of wire also carries an implicit valid signal. So if I don't assign a value to that wire within that clock cycle, then there's no valid data there, right? So in this case, so BSB FIFO enqueue val, that rule can only fire if I've assigned something to val in that same cycle. So another rule has to have assigned val to make this fire. And the FIFO has to be not full, and there has to be nothing else writing to the FIFO. All of that implicit. Yep.
So what happens what about when you don't care about what value val has, but you also don't care if it's enqueuing it anyway? There's a lot of code in Verilog where you can save logic by just not checking the valid signal because you don't care if it's valid. I still want to do this anyway because it has zero side effects. Are you now not able to do that kind of optimization because Bluespec?
No, you can do that. You have to do it in a different way from this.
Okay.
Yeah. Okay. So the key idea here is that methods, of course, can have side effects, and so they may be blocked from executing if those side effects are incompatible with something else going on in the system. And the nice thing is that the compiler actually sort of pushes those upstream. So if I call a method, if I have a rule that calls a method, that rule inherits all the implicit conditions to that method, implicit and explicit conditions of that method. And so not only is your interface, such as in Verilog, we have a write enable, a ready, and a data in, that method also, or the interface also encapsulates the logic of you can't enqueue to this when it's full. And that is actually carried along as well as part of the interface definition, which I think is pretty neat actually. And the compiler will enforce these for you. So it's actually not possible to enqueue a FIFO that's full. The compiler will simply not allow, the rule won't fire, and all the other stuff that's supposed to happen in your design when something enqueues also won't happen because the enqueue didn't happen. Right? So what actually happens at a hardware level, because obviously we have to synthesize this down to hardware, the compiler will make handshaking signals. So for every method in your module, there will be a ready output that says, my conditions are satisfied and I'm able to fire on the next cycle. And it will have an enable input that says, okay, now fire, and here's some valid data to fire with. And for debug purposes, it can also provide a can fire and will fire output. So can fire means condition satisfied, will fire means scheduler has decided this one's going on this cycle. So you can actually fire a model sim or whatever, look at your waveform viewer and see which rules are firing when. Fine.
Where does it make this handshaking signals? So you're saying, so what I mean is, you're saying Verilog designer must do this too, but you choose what granularity you're going to do this at in Verilog. You know, you can have a big module about type changes where only at the interfaces to it do you do that. Where does Bluespec choose to do this handshaking? Do you understand you're not handshaking between every individual register, for example. So
no, because registers carry no implicit conditions.
So how does it decide when it needs handshaking? Is it basically whatever is a module needs handshaking, or if you write the methods to basically imply that you want handshaking?
When there are implicit or explicit conditions, then there will be scheduling logic. And there'll be handshaking at each module interface.
Oh.
Okay? Okay. Does that make sense as an answer?
I think so. So does that mean all modules will handshake, or could I basically cascade a pipeline of modules where just the data flows through with no handshaking?
I mean, you don't need handshaking unless there are conditions. So if you make a module that has no conditions, then there's no handshaking logic.
Okay, so every block is going to do something that has no conditions and understands.
But I mean, if you have like a FIFO that can fill up or something, it provides an implicit method for back pressure. And the idea here is this sounds like extra logic, it sounds like overhead that's being imposed by the compiler, but to get a correct design, you have to arbitrate between the different things that want to change your state. Right? Like to get a correct design, you can't just jam two things into a FIFO in a single clock cycle. And so in Verilog, you have to decide what that arbitration logic is. In Bluespec, you tell the compiler how to prioritize between the different things that want to do this, and it will actually create the arbitration logic that makes it happen.
Follow up on that. Yeah, this goes back to your mod 3, mod 5 example. Let's say you want, you don't want to lose or drop any of the data. So when inside of hit 15, you actually want to enqueue either the 3 or the 5, and then delay the other guy, and then sometime later enqueue the 5 or the 3. Don't you then have to create arbitration logic in Bluespec to do that? It sounds like that's not what the normal way would do. So you have to explicitly tell it to do that somehow.
No, exactly. So this is where the C++ analogy comes in, right? C++, you only get what you ask for, right? It won't, the compiler will not automatically just build extra stuff for you. Bluespec likewise will not. So if you want to hold that value and enqueue it on the next cycle, that requires another state element. You must explicitly ask for that other state element.
Is it hard to do? Is it so? Okay.
Basically, what you could do is you could create create one rule that does the enqueue, create another rule that does that grabs the value, delays it, and then tries to enqueue it on the next cycle, and then you just say the first rule preempts the second rule. So if the first rule fires and the value goes into the FIFO, the second rule doesn't fire. If the first rule does not fire, then the second rule goes, grabs the value, and does the rest of your logic. So basically, if you want more state elements, you have to ask for them. And so on the one hand, that's very lean. You know what you're getting. You know exactly what modules you're instantiating. On the other hand, it is still hardware design. Okay? So I'll get into the type system really, really quickly. Again, it's inherited from Haskell. Type includes both signed and unsigned and bit length. And so you cannot just mix and match wire types, which is both sometimes a little bit more verbose, but it also stops you shooting yourself in the foot. Right? You can't add a signed with an unsigned unless you explicitly convert one into the type of the other and make them match. Likewise, you can't add a 4-bit to an 8-bit without extending or truncating as is appropriate. Although on interchange, it lets you be lazy where the type is obvious. Okay? So for instance, if you want to pull out the first element of a FIFO, well, my FIFO has a type that specifies what the FIFO holds. And so if you want to pull out the first element, well, you know that first element is of the type of whatever is in the FIFO. And so you don't need to tell it what R is because it will know. Or you can tell it what R is, and if it doesn't match, then it will throw an error at you. Okay? Really neat way of doing polymorphism. I know I'm running short on time here, so I'll try to condense this a bit. You can specify type classes, so you can create your own types, which are basically structs. They can hold data types of all different sorts. And you can create type classes. So a type class is a set of operations that a member of a type class must implement. So the simplest one, the simplest one is bit. So if you have a type class bit t, t is any type that can be represented by bits, for which you have a defined pack and unpack operation. Right? Arith t means the type t can have arithmetic operations defined on it. So somewhere someone has defined something that supports arithmetic. So in this example, I can create a function add3, which takes a variable type. So t is any type, takes 3 arguments, a, b, and c. Provisos means so long as t belongs to the type class arith. So as long as the arithmetic operations are defined for t, you can calculate a plus b plus c and return it. So this function will work on a uint 8, it'll work on a uint 65, it'll work on int, it'll work on any class you define that defines addition and is a member of arith. Make sense? And so you can get some pretty neat code reuse out of this, because this is sort of like C++ templates, but with formal checking that you actually have the correct operations supported. Alex?
What if you want A, B, and C to not be all the same type, but they be different types as long as they implement arith?
Yeah, you could do that. The only thing is that you would have to have a way of converting between the different types. So you could have T1, T2, T3, as long as T1, T2, and T3 are arith, and then you would have to do appropriate extend or truncate to make them all actually the same type. Because you can only add two things of the same type. So you can't do apples plus oranges, which Verilog will make some assumption that you get away with. So there's no implicit conversion. All right, so you can actually define modules and functions that accept any type. So you can actually create a module like 5.4 reg, where anything that can be converted to bits can be stuck in a 5.4 reg. But you still have the safety of that strong typing, like including things like let. So anything that you can create a type of your own that can be converted to bits, you can store that in a FIFO, and it will come back and it will still be typed as whatever your type is. So there's a lot of safety to that. You can do some neat stuff too, like you have polymorphic types. You can actually have types that take a type argument. So there's a type called maybe, which has a data valid signal. This maybe takes a tuple of two different types, T1 and T2, and return it as a method. So you can check if valid v. So maybe could be either what's called tagged invalid, which means data valid is 0, or it could be tagged valid and have a value. And then you can access that in various ways. Right, so Alex, your question here, you can do a default conversion here. So this is basically from maybe, so you're converting v from a maybe, and if it's invalid, it just gives it the type that's specified here. So you can put a question mark there for don't care, for instance, or you can put a default value. All right? All right. Couple handy little things here. This is pretty much the end of the code, so we're nearing an end. Hopefully the pizza gets here soon. All right. You can have a default register. So a default register resets to a default value every clock unless it's written to, which can be kind of nice. A wire is a physical wire, so there is no additional logic except for the implicit data valid signal. Right? You can also have an R wire. So a wire, if you have a rule that references a wire, it can only fire if another rule has already written that wire. You can also have an R wire, which returns a maybe. A maybe says invalid if you haven't written to the wire, and it says valid with data if you have written to it. So that's kind of, so here's an example of how a wire works. Right? So what we have here is a very simple accumulator. So it's got a register that accumulates. Oh, sorry, I missed one more type conversion. So basically the rule is you add the accumulator with whatever the input value is. I should have an extend on val in here. because you can't add a UN16 or a UN32 without extending the 16 first. I'll do that. We have another rule here that sets val to 10, and we also have an input method that sets val to the input value. Right? So what does the scheduler do for you? Well, it sees there's two writes here for val in, so it knows that there's a conflict between the two, and it also knows this rule can only fire when val in has been written. Right? So there's two ways for val in to get written. One is you call the method explicitly, in which case it writes to val in, and then this rule can fire and it gets added to the accumulator. Or, if the condition for this method is satisfied, it will set it to 10, and then because that's been written, that's valid, that rule fires. Right, so the idea here is that this accumulator is not free running. There is an enable signal that comes along with this signal val in implicitly. And so instead of having to do an if-then, you just write it up as rules, and the scheduler takes care of it. All right, so there's another one here. So this one, we have a value that may or may not be valid. So this is an illustration of dreg, a default reg. So you can see here, top line, dreg contains a maybe in 16. So it might or might not be an in 16. And the default value that it gets reset to on every clock is tagged invalid. So that register will hold the value invalid unless on the previous clock cycle something assigns something non-default to it. Right? So in this case, this is handy for, say, computational pipelines, right? So when you have, basically val in Q will always be marked invalid unless you call the put method. So you call put, it puts data in the pipeline and marks it valid. But then on the next cycle, that register automatically flips back to invalid. And then you have a signal here, delay iValid signal. Well, val in Q is a register. You can always read a register. There's nothing preventing you from doing that. So that will always fire. The register will always be readable, but you can check if it's valid or not. Okay? So then in terms of libraries, what do you get for free with BSV? So I've been showing, of course, a lot of FIFOs because it's a classic example. They also have VRAM libraries for FPGAs, gearboxes. So if you're going between clock rates, that is already provided for you. They have a fixed point library, synchronizers, grade counters. They also have some bus IP, which is where I think Bluespec really excels, dealing with buses. Instead of writing and reading a whole bunch of ports, you have methods. Post this to the bus, read this from the bus. Very handy. And they also have a very handy sequential language for finite state machines. So you can do for loops, you can do while loops, and it will actually generate the correct logic to do that for you. Right, so the workflows, you can take Bluespec and a C model. It will compile that to a .o file, and it will run it in Bluesim natively. So it will actually produce native machine code that runs really, really fast. It'll include assertions. You can control interaction with tickles. So kind of like in model sim, you can step, you can inspect values and so on. The only drawback is you need to replace any Verilog code you have with a C functional model. You cannot integrate Verilog into this compiled flow. You can do BSV, Verilog, and C. It'll compile that to Verilog with VPI. It'll automatically generate the wrappers, and you can stick that in model sim and do all the stuff that you do in model sim, including looking at the can-fire and no-fire signals. So it gives you a really, really fine-grained simulation if you want. The drawback being it's slow, right? About 10x slower. And of course, BSV and Verilog can be synthesized together and then thrown into your FPGA tools and give actually pretty decent results. I have looked at the code a bit, and you can actually recognize your hierarchy, you can recognize your signals, you can see your enables, can-fires, will-fires. And so it actually gives you a pretty decent window into what the synthesis tool is doing. And so you can actually trace back from a synthesis error or a synthesis warning to see what the heck is going on. Generally, I found it wasn't generating synthesis warnings. It was generating correct code that the vendor tools liked, which I thought was pretty nice. And of course, it was also high-performance code, too. So to sum up, because everyone can smell pizza, strengths, it gives you a variable level of abstraction. You want to get down to the meta level, you can do that. If you want to write a very rough functional model, you can do that. If you want your functional model to play with your synthesizable code, you can do that. It's at least 10x faster than model sim. It's concise. There's not a lot of new syntax to learn. It integrates cleanly with C and C++, and it gives you readable output code. I did run into some issues inferring sign multipliers in Altera, because of the way the sign extension, you can work around it. The built-in file I/O library is not great, but I wrote my own in C++ and integrated that. It was minimally difficult. They do support fixed point, the conversion manual. There's no getting around that with this particular tool. And you can't use Bluespec as Verilog code included. But I mean, on the upside, I learned a language and wrote a thesis project of 4,500 lines in 6 months. It works. I have every confidence that it's maintainable and I can scale it. Performance and area, I do not think I could have done better writing Verilog, and I think I'd still be writing it. It's far more productive. You're writing less code. The compiler is giving you intelligible errors. It's telling you why your design is logically incorrect instead of why, you know, you're writing to this wire twice, but I can't tell you why that's happening. And it gives you fast simulation. It's great for control-intensive tasks, NOx, switches, routers, processor design. I think it's a great target for latency and sensitive techniques. FIFOs are a first-class citizen. You don't need to go out to the mega wizard to instantiate a FIFO of a given depth. It's a single line of code. And what it synthesizes is fast. So very handy in that sense. Simulate quickly, you can refine and explore lots of architectures, and I found it's a very rapid return on investment. As I said, it was jittery. You know, in March, okay, got to have a thesis done in the fall. Going to learn a new language and write a thesis in it. Worked out great. You could write Verilog, or sorry, write BSV the way you write Verilog initially, and then you can start getting into the tricks. So it's not a complete build from scratch. I'll leave it there. Thank you very much. Yeah, just email me if you want to get into this and try it out. I highly recommend it.